Hello, this is a skin text. Although the video that is supposed to record this in has already been recorded, but I don't know. Sounds like a fun time to skin test. Anyways, hello Cyrus. Here's the solution for threesome. Before that, well, we probably don't need to go through the question description, so I'll just go through it a little bit. Given an integer array nums, return all the triplets of elements in the array such that they have distinct indices and they all sum up to 0. Try to return a list of all triplets. The thing about Leetcode is that it also only asks for when it asks for a list of something, it also generally accepts an iterator or something. So I'm just going to exploit that a little, but it's not gonna cause too much. Not gonna cause too much problem to our solution. This is the general run through I had with my solution, which I will erase all of it so that I can talk about it again. Let's look at this test case here, which is the first one, where I have an array nums. That is just as spoken above, and we can see the different tuplets that work because each of the triplets have elements of distinct indices, and they all add up to 0. Furthermore, these triplets do not have duplicates inside the array, so our list of returns should be a list of distinct tuplets. Now I'm going to present two solutions. One uses two hash maps, and the other one uses the two-pointer solution, which I previously sent. But all of these solutions can benefit from generally sorting the array. Now we know that the naive solution is that we go through the original array and use 3 pointers and try to look at every single possible combination of the three indices in the array, such that we only record those that add up to 0, and such is the original spirit of the question. But this algorithm sums up to be O of n cubed, which just takes a lot of time. So, well, arguably, O of n cubed algorithm probably takes more time than the amount of time it takes for our apartment to pay our rent. So why not sort the array? After sorting the array, what I can do is, for every single starting indices, what I do is I then perform a two-sum problem on the rest of the array, which is supposed to have a complexity of O of n. So this entire algorithm sums up to be O of n squared. Battery saver is on. Okay, so now I have a general sketch of the algorithm. Let's try to code it up. And I also know how to solve two-sum, but since I'm dealing with a sorted array, there's actually now two efficient ways of solving two-sum. One is using hash maps as usual, and the other one is using a two-finger algorithm. Let's write down the general sketch of the algorithm, and then we can just not deal with this. Actually, let's just do this. Okay, we need to first sort the array, and then for each starting indices, perform a two-sum. Record all possible solutions, and return. Step 2 and step 3 are most likely an iterative process. Alright, and there's also an interesting thing about array equality, which is that if the elements of an array are equivalent and they're sorted in the same order, then the arrays will be treated as equal to each other. Same for tuples. So I'm just going to piggyback off that and use it in my solutions when I'm trying to define the solution as a set of tuples or list. I'll also remember to sort my nums. Okay, from here, let's write out the general sketch of the algorithm and then we can deal with the two different ways of solving two-sum. Generally, for each starting indices, I would like to first try to have an overall solution of two sums. So that being said, I would probably have a helper method here that helps me do the two-sum problem. Return all tuplets in nums to target. Return. For now, I'm just going to put a return here. Okay. So I'm going to have all tuples be the solution of two-sum from nums, from the rest of nums to, well, my target, the sum of, oh my god, the sum target of my tuple, or the target number that my tuple should sum up to, is equal to the negative version of my currently acquired element. Because that way, only in that way will all the elements sum up to 0 and cancel out. And then for all of the elements in all tuples, I would then like to add to solve these solutions. Note that lists are not hashable, so we are going to use tuples here. And since our array is sorted, I can safely use this syntax. Finally, return sols. Or if you're really picky, return list of sols. But I'll just return sols because Leetcode accepts these kind of things. Okay, now that we have a general sketch of the algorithm, it's time to write down the two-sum sum action. I'm going to go off the hash map solution first. Which would probably be a memorizable thing. So I still have a set of solution because I need to return all tuples that work. And I also have a hash map for me to record the instances I'll come across in this two-sum method. And then for each starting indices of the nums array, if I have a counterpart existing in my currently sin elements, then what I will do is to add the solution, which to sort a for me to sort a two-element array or a two-element tuple, I'd rather just write it as having the first element be the minimum and the second element being the maximum. It seems a bit easier to do that. This procedure will reflect with why we're using the syntax here is because we're adding tuples together. This comma makes this thing a tuple. If without the comma, it's going to be an integer. Okay. We'll also have an else class to counter off the situation where we cannot find our complement index. Unless we return so. Okay. So this is the way of threesome that should work with two hash map. We can do a primary debug to test that out. Name twosome is not defined, and that's because I forgot to say the self dot. What else? What other stupid bugs are there? Oh, okay, so they are accepted for now. Let's see how they work in submission. So this one is accepted, it seems. Yes, this one should be accepted. Okay, so that's the way to write it with two hash maps in total for the entire solution. Now, what is the two-finger solution then? Well, the two-finger solution would be a bit easier. It will have less space complexity because it only uses 2 pointers instead of a whole hash map. So granted, that's going to look a bit easier. In this case, sol is still equal to a set for I in range length of nums. Actually, I don't even need that. I'll first have a head pointer and a tail pointer. So that the way in which my two-finger solution is going to work is I'm going to try to find the subarray that, for example, adds up to -4. So for example, currently I am working with a tuple that is -1 and 2 and sums up to 1, which means I need more value. If I need more value, which means if the current sum is less than target, then I'll move the head pointer right by 1. Otherwise, I'll move the tail by left. I'll move the tail pointer to the left. Okay. So while the head pointer is still less than the tail pointer, since they both stand for indices, if nuns of pointer head plus nuns of pointer tail is less than the target number, then I will move the pointer from the head right by 1. And what I'll do instead, if the opposite happens, is I'll move the tail by 1 left. This should be an L of you. And last but not least, if none of those happen, then they're equal. And what I'll do instead is to add the tuple to the solution. Remember that this is a sorted array, so I can do this safely. Okay, and last but not least, I will still reduce the tail pointer by 1 because I need to make sure that I keep going onto tuples that can possibly work. Okay, and last but not least, I'll return sol. Okay, let's see how this runs. Accepted, accepted, accepted. Let's see how this emission works out. Alright, and that's the... Well, as you can see, the memory is working pretty well here. Time is not working pretty well, but I genuinely do not care about this on a Christmas Eve.